Wait, is this working recording?
Okay, so here's the plan for today. We're going to finish up this review packet and kind of show you some differences, finish up pH, that type of thing. Weak acids versus strong acids. And then that'll finally be put to rest, and we'll transfer that into like a more complex discussion of just weak acids. So don't forget Wednesday, first quiz, okay? A lot of it's going to be, almost all of it's going to be off of this review packet, so make sure that you got that. That quiz on Wednesday, you're going to need to know just 4 of the strong acids, the formulas, and the name, like nitric, sulfuric, whatever, okay? Pick whichever 4 you want. Now, so you kind of have to understand on like the mechanics of what happens when we measure pH. So here I've got, now this is like the old school, it's still digital, but see here I've got a pH probe, and the ones you guys are going to do, you're going to hook those up to LabQuest, but it's still the basic idea. So basically what happens is that that electrode in there measures how well it conducts electricity. And then that translates into basically an algorithm, and it says, okay, hey, here's the pH level. So what I have here, and I'm going to have 2 different solutions. They're both going to be 0.1 molar. So here I have a 0.1 molar of acetic acid, which is C2H3O2. And we're going to spend a lot of time talking about acetic acid, mainly because it's cheap, it's a very known value. We're going to do a whole like 3-day titration with acetic acid. Okay, we're going to use it to make buffered solutions because it's basically vinegar. So here's what's going to be important, is that this is a 0.1 molar solution of acetic acid. So in this pH, when I read that, is 4.36. So if I want to get an idea of what's the actual hydronium ion concentration in this beaker, I said, okay, great, we have this pH. So there's a whole bunch of different things once we get that pH. So one thing is, if you notice that pH plus POH add up to 14. Okay, and the reason those add up is because at standard conditions, 25 degrees Celsius, your hydronium ion concentration times your hydroxide ion concentration equals the autoionization constant, which is 1 times 10 to the negative 14, which works out well, okay? Luckily, Mother Nature kind of liked nice numbers. It isn't like that was like 3.16 times 10 to the negative 19, okay? It was a nice number. Mother Nature smiled on us and said, hey, let's make this simple, okay? And we didn't arbitrarily pick this number. I mean, that's in neutral water. This hydronium ion concentration is 1 times 10 to the negative 7. Your hydroxide ion concentration is 1 times 10 to the negative 7. It happened to work out that way. It isn't like we picked the scale to set it up that way. We got lucky, okay? If there's any computation in chemistry that we got lucky on, this one we got lucky on, just because it makes the math easy. So, in this case, I know my pH is 4.36. So, how can I find my POH then? Yeah, don't make this difficult, right? So, if I take 14 minus the 4.36, I get 9.64. So, there's my POH. Because my pH times my POH always have to add up to 14. Okay, and again, it's a nice number. It isn't, I'm not making it add up to 16.35. Okay, it adds up to 14. Boom, there you go. So if I actually want to find the concentration of my hydronium ions, I know my pH is 4.36. So to get my hydronium ion concentration, somebody can get out a calculator. So I'm going to take 10 to the negative 4.36. So here's the deal. Here's the significance of that negative sign. The reason that we have to have that negative sign is my hydronium ions and my hydroxide ion concentrations are both very small numbers. If I take 10 and raise it to the positive 4.36, I'm going to get like 10,000, okay? I'm not going to have a molarity of 10,000, okay? It's not even remotely possible, okay? Not even. Highest concentrated molarities are around 16. if you ever calculate molarities and you get like 1,000, you have done something horribly wrong, okay? Horribly wrong. And remember, this is also figuring out the secret code. When you see those brackets, no matter what it is, when you see those brackets, you're talking about molarity in moles per liter. So if I wanted the concentration of my hydroxide ions, I would put those in square brackets. So part of this is reading the code. Okay, when you see the square brackets, so what does that mean? So somebody take 10 to the negative 4.36, what do you get? Scientific notation.
4.36 times 10 to the negative fifth.
Times 10 to the negative fifth, and that's going to be my molarity. Okay, so there's the concentration of my hydronium ions. I could also find the concentration of my hydroxide ions. Now, this is a personal preference on how you do this. Makes me no difference. If you wanted to calculate the concentration of your hydroxide ions, you could take 10 and then raise that to the negative POH. So you could take 10 to the negative 9.64, and you could get that number. So if you like anti-logs, that's an option. You go, Mr. Burkham, I hate logarithms. Okay, I'm a tree hugger. I hate logs. Okay, cool. Your other option is that you take 1.0 times 10 to the negative 14th, and you divide that by your hydronium ion concentration, and you can get it that way. Okay, this is probably a little bit simpler because all you have to do is take 10 to the negative 9.64. Yes?
So for hydronium ions, it's normal to get very, very small numbers.
Yes, especially if it's an acidic solution. If it's a basic solution, then they switch. Then your hydronium ions are very small and your hydroxides are very large. Okay? So, both on any time when you're finding hydroniums and hydroxide ion concentrations, they're typically very small numbers. So, that's all we can do with this. So here's in contrast to this. This was a 0.1 molar solution of acetic acid. Acetic acid is a weak acid. So what that means is this. And on an atomic level, when you talk about weak acids and acids in general, a lot of times what we do is we abbreviate it as HA. HA is just a generic way to write an acid, okay? It just saves us writing everything out. So technically acetic acid is HC2H3O2. Okay, that's technically the big long formula for acetic acid. A lot of times we just abbreviate it as HA. So this is why when you look on your equation sheets, you'll see like HA. That's what that's talking about. It's just a generic acid. Okay, so don't flip out on this. So there's two ways that we can talk about what's going to happen. One is the shortcut version, and the other one is the more technical version. Which one do you want first, the technical version or the shortcut version?
Technical.
Technical. Okay, we'll do the technical version first. So what happens on the technical version is that technically there's a whole bunch of water molecules around here. Okay, we talked about this yesterday. You're understanding all of this. You really need to understand what happens with water molecules because the water molecules are the story. So you've got the hydrogen end, which is positively charged, and then you have the oxygen end, which is negatively charged. So what's going to happen is that you take that acetic acid, and it's going to come up to the water. And the acetic acid is like a tug of war. So what's happening is that there's a hydronium ion here, it's positively charged, and that's attracted to the negative end of the water molecule. The anion, okay, which is the negative part, is going to be attracted to the positive. So it's a tug of war. So it's like you go to prom, and you're there with your date. And you all are, as soon as you get to the prom, now there's a tug of war. It's like, oh man, all my friends are over there. I kind of showed up with my date. It's like, oh, what do? Do I go hang out with my friends, or do I stay with my date? Okay, that's the moral quandary that you all run into when you go to a dance. That's the quandary. Like, ooh, what do I do? Okay, so if it's a weak acid, what's for the weak acid? What that means is that I'm going to put first off a double set of arrows. When I put the double set of arrows, that means that this reaction can go back and forth. It doesn't always go in one direction. This reaction can go back and forth. And so what's going to happen is that we're going to form some hydronium ions. So what's going to happen is that this hydrogen is going to spend some time attracted to the water. So in other words, it's going to go over there, it's going to hang out with its friends. Okay, it's like, oh, look, there's the water molecule, right? Form hydronium ion. And then the anion is going to be left behind. Okay? So what's important when you work with pH probes, and you're going to spend a lot of time working with pH probes, you have to look at what these pH probes measure. The pH probes don't measure the anion concentration. Here's the reason why. Because we don't want to have separate probes for every potential acid. I don't want to have a probe for hydrochloric acid to measure the chloride ion concentration. I don't want to have one for nitric acid, which measures the nitrate ion concentration. It would just be insurmountable, because we'd have to have probes for every acid if we wanted to measure the anion concentration. So what we did is said, okay, let's make this simple. What's the simplest thing we can measure? Oh, we can measure the hydronium ion concentration, because that's going to be the same no matter which type of acid that we deal with. So this is why we measure pH, because that's common to every different type of acid in terms of how it ionizes. This is why we don't measure the anions. This is why we measure the hydroniums, because those are all the same. Otherwise, we'd have to have separate probes. Okay. So what's going to happen is this. You have a 0.1 molar solution of acetic acid. So here's my rice chart. Okay? So I have a 0.1 molar solution of my acetic acid. That's what I started with. Literally, I mixed this up before class. I mixed up a 0.1 molar solution of acetic acid. This is what I started with. So initially what we're going to assume is that all of these values over here are 0. So we're going to assume that I have no hydroniums and I have no anions. So this is you showing up to prom. This is the initial set of conditions. You show up to prom and you are with your date, okay? And you haven't had a chance to ionize yet. Everything is 0. So what's going to happen if it's a weak acid, and we'll contrast this with a strong acid. So what's going to happen on a weak acid, and this is basically what I'm going to work here on this last page in question number 12. Okay, so this is what I'm going to work through. The only difference is that it's a 0.02 molar, this is a 0.1, it's going to be the same process. So here's the assumption that you make. If it is a weak acid, only some of this is going to ionize, because, and here's the reason why. That anion has a very, very strong attraction for that hydronium ion. Okay, so this is like you show up to prom and you are with your soulmate. Okay, you two have been going out for years. It's a very, very strong bond. You might ionize for a little bit, like you might go over and say hi to your buddies, but you're going to come right back. Okay, so you might ionize for just a small amount of time, but not for very long. So what's going to happen is that we're going to subtract some value of x, okay? I don't know what it is. I'm just going to call it x, because I'm going to ionize some of this. Not very much of it, just an x value. So then I'm going to put plus x plus x. So this becomes 0.100 minus x. This becomes x, and this becomes x, okay? Now, here's the most important thing. So if you look on your equation sheet, you have this handy-dandy little equation that says Ka equals your hydronium ion concentration times your anion concentration divided by HA. This is what's on your equation sheet. Now, if you understand and listen very carefully to what I'm about to tell you, Ka calculations become very simple, but it hinges on one important thing. And that's that value of K. We're going to use K values a lot. Ka, Kb, Ksp, a whole bunch of different things. So anytime you see an uppercase K, it's kind of a Zen thing. That means that the system is in equilibrium. Okay? Everything is well and right with the universe. The system's in equilibrium. Okay? And that's what Mother Nature wants, because Mother Nature is a lazy prima donna. Mother Nature wants to be in equilibrium. She wants to sit back, toke on a hookah pipe, wear her tie-dye with her gray hair, and just chill out. She doesn't want to be out of equilibrium. She just wants to chill out. And that's what Mother Nature wants. Mother Nature wants to be in equilibrium. But different reactions have different K values. So if you look on, somebody had their book. Let me see. Look. So what's going to become your friend? Okay, thank you. Back here in the back, you're going to have an index. It's going to have right here on page 1092. You have all of these acids listed and all of their Ka values. So you have Ka1, have Ka2, and then you have Ka3. So notice that they all have K1s. So K1 refers to the equilibrium when the first hydrogen ionizes. That's what that K1 means. Now, some of these have a K2 value. Notice not very many of them have K2. K2s happen with what we call diprotic acids. Diprotic acids are when you have a second hydrogen that you can pull off. And very rarely do you have a Ka3 value, which is a triprotic acid, which is like phosphoric acid, which is H3PO4. So you have Ka1, Ka2, K3. What we're going to deal with 99% of the time is going to be that first column of Ka values. Now, you'll notice that Ka values change. Like, for example, acetic acid, 1.8 times 10 to the negative fifth. Some of them are very, very small. Like you have phenolic acid, which is like 10 to the negative 10th. Okay? You have some are 10 to the negative 11th. So these K values change depending upon which acid that it is. But here's what's important. Is that Mother Nature, above all else, mathematically wants the product of that hydronium times that anion divided by that HA, no matter what. Mother Nature wants to be in equilibrium. Okay, that's the driving force. Mother Nature wants to be in equilibrium. So here on page 12, I've given you the Ka value of acetic acid, which is 1.8 times 10 to the negative fifth. Now, it's rare that this happens. But Ka values have no units. Okay, there's nothing associated with this. It's just a number. Okay, mainly because the units get all screwed up. So it's just a number. Don't worry about it. This is one of the very few times I will ever tell you that it's just a number. There's no units associated with it. But here's what I want you to see: is that Mother Nature, under any circumstance, wants the product. If you have acetic acid, that hydronium times that anion divided by the concentration of that acid, Mother Nature wants that mathematical value to equal 1.8 times 10 to the negative fifth. And Mother Nature is going to do whatever it takes to get that situation to here, 1.8 times 10 to the negative fifth. So when you have this, and again, it's simple, but it's an important concept. When you see that value of K, right away, oh, that's an equilibrium. So what that means is that what you put into that calculation is going to be the equilibrium line. Not the initial, not the final, but that equilibrium line. Okay? That's hugely important. The only number that ever goes in here on a Ka calculation is your equilibrium line. Not where you start, not what you change, but it's where you end up. Okay? Now, so at this point, what's going to happen, the only thing different on number 12 is that this is going to be 0.02. Okay? So if you're going to work number 12 on that back side, the only thing that changes is that this is going to be 0.02. Now, here's the deal. That Ka is going to equal that hydronium ion concentration, which is going to be at equilibrium. This is going to be X. Okay? I don't know what it is. It's just X. Don't know, it's just X. My anion concentration, because of the fact that it ionizes in a 1-to-1 ratio, is also X. That's it, it's X. Boom, there you go. Don't make it complicated, they're both X. Now, technically, this is, if you're working number 12, technically that's 0.020 minus X on the equilibrium line. Now, here's the problem. And we're going to make this simple unless I tell you to make it complicated. You are always going to assume that this is simple. When you multiply X by X, oddly enough, you get X squared. Okay? Not a difficult concept, you get X squared. So unless I tell you otherwise, you assume that the subtraction of that X isn't enough to alter that value of 0.02. So in other words, it'd be like you go to the ocean and you take out a spoonful of water. Did you technically change the volume of the Pacific Ocean? Yes, you did, because you took a spoonful of water out of the Pacific Ocean. Okay? Is it really going to make any difference? No. Okay? So now, but if you have a beaker of water, and you take out a spoonful of water, oh, that's going to be pretty dramatic. So what we're always going to assume, unless I tell you differently, that X, you don't have to worry about subtracting it. Okay, and it's technically what's known as the 5% rule. If your amount of ionization is 5% or less, the subtraction of that X doesn't matter. Okay? Now, if it does matter, and you're going to have a problem like this on your assignment, then you have to work it as a quadratic. Because then, in that situation, what you've got to do is leave that as 0.020 minus X, and then you have to solve it as a quadratic. I'm only going to make you do that one time. I will never make you do it on the test, but it's just so you see the significance of when you need to do that. So this is just going to be 0.020. So at this point, I know what my Ka value is. I gave you that number. So I got 1.8 times 10 to the negative fifth equals X squared divided by 0.020. Technically it's minus X, but we're not going to worry about the X. Not worth it. So here's my question. Gracie, how am I going to get X by itself?
Multiply by 0.02.
So I'm going to take my Ka value multiplied by 0.020, and then what?
Square root.
Then I'll take the square root of that. Okay? So somebody take 1.8 times 10 to the negative fifth times 0.02 and then take the square root of that. What'd you get?
6 times 10 to the negative 4.
6.0 times 10 to the
Negative 4.
negative fourth. Okay. Now, at this point, you have to understand what that X is telling you. Okay? So that X actually tells you two things. It tells you your hydronium ion concentration, and it tells you your anion concentration, because it's a 1-to-1 ratio. So what we're saying is that at equilibrium, Mother Nature wants both of those X values to be 6.0 times 10 to the negative fourth. So that equals your hydronium ion concentration, and it also equals your anion concentration. Okay? That's it. There you go. So now I know what my hydronium ion concentration is. Now I can find my pH. So now my pH is going to equal the negative log of my hydronium ion concentration, right? Which in this case is going to be the negative log of 6.0 times 10 to the negative fourth. And what do you get?
3.22.
3.22. Okay? So that gives me my theoretical concentration of my hydronium ions, and it also tells me what my pH should be. Okay? Cool with this. Now, that's if it's a weak acid, okay? That's if it's a weak acid. So if you want to find that last step on that percent of ionization, here's what you're going to do. You're going to take your anion constant or your hydronium ion concentration. So to get your percentage of ionization, that's your hydronium ion concentration divided by the initial concentration of the acid times 100. So that's going to be 6.0 times 10 to the negative fourth divided by 0.02. Technically, these are molarities. And then you multiply that by 100. So what do you get?
3%?
Huh?
3%?
3%. Okay? So, what that means is if you were a couple and you go to prom, that means that 3% of the time you're going to be ionized. 97% of the time you're going to be existing as a couple. So, by definition, what makes something a weak acid is that it doesn't ionize very much. Okay? So, when you look at weak acids, you talk about where the equilibrium lies. So what this means, because it doesn't ionize very much, what that means is that when you look at this reaction of this acid reacting with the water forming hydroniums and anions, what that means is that only 3% of the time it's ionized. Only 3% of the time is it over here. 97% of the time it exists as what we call the molecular form. So you go to prom. 97% of the time you are with your date. Only 3% of the time are you separated. Okay? Got that idea? Now, here's the contrast. So now I have a 0.1 molar solution of hydrochloric acid. Okay? Now, so this pH was like 4.3. This is the same molarity, 0.1 molar. But if I measure this pH, that pH drops like a rock. Okay? It drops all the way down to, and still dropping, 2.56. So even though they're both 0.1 molar, even though they're exact same molarity, the hydrochloric acid has a much lower pH than the acetic acid does. And here's the fundamental difference, okay? So when you take hydrochloric acid or any strong acid, you take hydrochloric acid and you put that in water. It's still going to be the same thing. You're going to form H3O plus the anion. The reaction, the R value is the same. Okay? Now here's the difference. In this situation, when you set up your rice chart, it still starts the same way. That's, in this case, this is a 0.1 molar solution, 0, 0. Now, here's the story. What happens in contrast with the strong acid is that the hydrochloric acid, when it gets in the presence of the water, basically says, hey, I'm outie. I'm going to go hang out with my mates. You are on your own. Find me if we need to take a picture together, but other than that, I'm out. Okay? We are going to prom as literally the utmost definition of just friends. Because as soon as we get to prom, we are going to completely ionize. I don't even know you unless you want to take a picture. Otherwise, I'm out. Okay? I am going to be hanging out with my friends. Because here's the reason why. That hydrochloric acid has a much stronger attraction for the water molecule than it does for itself. It's like you go to prom, you have a stronger attraction for your friends than you have with your date because you guys just showed up, we're just friends. Okay? So what's going to happen is that all of this is going to ionize. Okay? Or basically like a huge percentage of it. We just assume that it completely ionizes. So this becomes 0. Okay? 0. Or at least a really small number. Okay? They might get together for a picture, but that's about it. They're fundamentally going to be ionized. So then, over here, I'm going to add 0.1. I'm going to add 0.1, and this becomes 0.1. Now, here's the significance of this, okay? If you look at your book and you look on the Ka values, you are not going to find a Ka value for strong acid. So whatever you do in calculations is a major faux pas. Do not go, oh, Burkamp, what's the Ka of like nitric acid or hydrochloric acid? It doesn't exist. And here's the reason why. Mathematically, if you look at the Ka value, which is your hydronium ion times your anion concentration divided by HA. So even if you wanted to, you say, Burkamp, I want to find the Ka of acetic acid, or of hydrochloric acid. Cool, good for you. Good for you. So I'm going to have basically 0.1 times 0.1 divided by 0. What do you when you divide by 0?
Undefined.
Undefined. Okay? Or let's say that it does exist for a little bit. Let's say it's 0.00001. Let's say we have a little bit, just a tiny, tiny bit of the molecular form of the acid. So Morella, take 0.1 times 0.1 and then divide that by 0.00001. Let me know what you
How
get.
many zeros? 5?
4.
Okay. 1,000.
1,000. Notice that that's a huge number. This is why you don't have Ka values for the strong acids, because either they're undefined or they're huge numbers. Now, later on, once we get into thermodynamics, you're going to see the significance of very small numbers. What that means is that when you have very small K values, whether it's Ka, whether it's Kb, whether it's Ksp, we're going to deal with a whole bunch of them. Very small K values, like less than 1, indicates that the reaction is not favored in the forward direction. So I'm just going to plant this seed. We will revisit this again and again and again. This is just the opening shot. So whenever you see a K value that's really small, that means it's not favored in the direction in the forward direction. It's favored in the reverse direction, so equilibrium lies on the left. Now, so here's the deal. So the Ksp value, or the Ka value of acetic acid, is 1.8 times 10 to the negative 5th. Now, somebody open up that book to page, whatever that was, 1,000, whatever that is. And find me find me the Ka value of hydrofluoric acid. HF. The Ka value of hydrofluoric acid.
6.8 times 10 to the negative 4th.
Okay? Now, find me one that's really small, like 10 to the negative 8th, 10th, something like that.
Hydrogen peroxide is 10.4 times 10 to the negative 12th.
No, don't do hydrogen peroxide, because that gets weird. Like an actual acid one.
Like 1H?
Huh?
Like 1H? Is H2O2, does that have the 2?
Yeah, but it's weird because it's hydrogen peroxide. Technically, it's an acid, but
Why is it weird?
It just is.
Oh.
Arsenous acid?
Huh?
Arsenous acid is 5.1 times 10 to the negative 10.
Okay. Now that's arsenic acid.
Yeah. Arsenous.
Arsenous.
Okay.
Arsenic?
Now, here's the big picture. Here's another big picture. If you look at Ka equaling your hydronium ion concentration times your anion concentration divided by the concentration of the acid at equilibrium, this turns into a mathematical problem. Okay? So here's the deal. Arsenic acid has a Ka value of 5.1 times 10 to the negative 10th, which is a really small number. Okay? So that means with arsenic acid, these numbers up on top are really, 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 really small, okay? And the number down here has to be relatively big. So what that means is that if you have a really small Ka value, that means that this stuff doesn't ionize hardly at all. Because the only way that I can produce a really, 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 really small value of Ka is if my top numbers are really, 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 really small, and the bottom number is really, really, really big. So now, if you compare that with hydrofluoric acid, 6.8 times 10 to the negative 4th, that's actually a relatively large Ka value, okay? So the one thing that's unique about hydrofluoric acid, if you go down the acids in the halogen groups, hydrofluoric, hydrochloric, hydrobromic, hydroiodic, hydrofluoric is the only one that's a weak acid. All the other ones are strong acids. Okay, so this is what makes that unique. So even for hydrofluoric acid, this 6.8 times 10 to the negative 4th is a relatively big number. So what that means is that these hydroniums and these anions, even though it's a weak acid, it ionizes more than the other ones. So here's the story. So if you want to create a big Ka value for a weak acid, that means that it ionizes a lot, okay? If you have a very, 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 very small Ka value, that means that it doesn't ionize very much at all, okay? See that difference? So, when you get to this question on number 12, what's the difference between weak acids and strong acids in terms of the ability to ionize? If you understand this, strong acids completely ionize. And here's the dichotomy. Strong acids have an exceptionally weak bond between the anion and the hydronium ion. They will ionize, boom, I'm out of here, see you, gotta go, love to chat, I'm out. Weak acids have a strong bond between the anion and the hydrogen, and that's why they don't ionize very much. So if you want to overlay this thought matrix to prom, okay? You show up to prom and you're just friends. That means you are easily going to ionize and you're going to spend most of your time as separates, okay? You don't have a very strong bond with your mate. You show up to prom, boom, we're going to ionize. In contrast to that, it's, if you've ever seen the movie Princess Bride, it's love, true love. And if you have a really, 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 really strong bond with your date, okay, you're not going to ionize very much. So there's an inverse relationship. So the stronger the bond between the anion and the hydronium ion, the stronger that bond is, the less it's going to ionize. The weaker the bond is, the more it ionizes. So that's that dichotomy. Okay? Now, here's the shortcut way of how we deal with acids. Instead of going through this rigmarole of writing the water and everything, typically here's what we do. We just go, HA turns into hydronium ions and anions. Okay? That's the shortcut version. Technically, there's water. Technically, those are hydronium ions, but we just shortcut it, and we leave the water out of it. So this HA turning into hydronium ions and anions is the same thing as saying the acid plus the water yields hydronium ions and the anion. Okay? So this is technically more correct. Okay? But typically that's how we write it because chemists are efficient. Some might call it lazy, but let's just call it efficient. So these two things mean the exact same thing. Okay? All right. Now, let's talk about that last 1% to formula. Okay? I want to make sure everybody's cool with this. So, if you look at how we figured out the different formulas, okay? Methane, CH4, methanol, CH3OH, okay? All these different compounds. it isn't like Moses came down and he had the 10 Commandments on one side, and on the back side was the periodic table and all the structures of all these molecules. Okay, would have been cool, would have saved us a lot of heartbreak. Okay, that didn't happen. So one of the techniques that you do is you take a compound, because again, you know, we talk about water and we build these nice little molecules and it looks like it's static. Like, oh, look, it's a little Mickey Mouse and there's ears on it and there's the oxygen. We can look at it. And if we look really close, we can see the word oxygen written across there. And we can see hydrogen written up. No, okay? These are electron clouds and it's a nucleus, okay? We can't see it. We can use X-rays, we can do some different techniques to actually find the structure. But so what we typically do is we break it down based upon percentages. So what's happening on number 13? I give you a compound and you separate it. You break the bonds and you separate it out, okay? And you say, all right, based upon this, I know this compound is 25.9% nitrogen and 74.1% oxygen. We want to find the empirical formula. So remember, empirical formulas are the simplest whole number ratios. Molecular formulas are multiples of the empiricals. The molecular is, hey, what does this thing actually look like? Empirical is just the simplest ratio. So here's the deal. The easiest way to approach this problem is to assume that you have 100 grams of this sample. Okay, that's the easiest way. I'm going to start off and I'm going to basically say, hey, I got 25.9 grams of nitrogen and I have 74.1 grams of oxygen. That's the easiest way to do this. Okay, you can make it 0.259 and 0.741 if you really want to do that. If you're in this work camp, I'm into decimals. I was president of the decimal club in high school. Good for you. Happy for you. Okay? Make it 0.259 and 0.74. It's all going to work out to be the same anyway. I don't like decimals. That's why I just do it as a percentage. Now, here's the bigger picture. You're trying to find this formula, some ratio of nitrogen to oxygen. Now, listen to me very carefully. That ratio is a ratio of two things. It's either a ratio of particles or it's a ratio of moles. It is not a ratio of mass. Okay? It is not a ratio of mass. And here's the reason why. Let's say that you have water, H2O. Cool, right? If I have 200 hydrogen atoms and 100 oxygen atoms, is it still the same ratio?
Yeah.
Yeah, so 2 to 1 ratio, right? If I go 2 million and a million, still the same ratio. If I have 2 Avogadro numbers of hydrogens and I have 1 Avogadro's number of oxygen molecules, is it still the same ratio?
Yes.
Still the same ratio, right? Well, if I have Avogadro's number of oxygen atoms, oh, that's 1 mole. If I have 2 Avogadro's numbers of hydrogens, oh, that's 2 moles. So that's why these formulas are ratios of atoms and they are ratios of moles. They are never, I repeat, never a ratio of mass. This is why you have to convert them into moles. So, come in here, 14 grams, 1 mole, oxygen is 16. Now, the reason that we're using 16 and not 32 is because you don't know if this is collected as a gas. You weren't told that it was specifically like oxygen gas. You just know that it's oxygen. So since you weren't specifically told that this is oxygen and nitrogen, that's why you use 16 and 14 and not the diatomic versions of this. So if you do this math, you get 1.85 moles of nitrogen and you get 4.63 moles of oxygen. Now, I cannot emphasize this enough. You have to get in the habit of writing down what these numbers are, okay? If you just put 1.85 and 4.63, You don't have an idea what these are, and I don't know what they are. You have to put units on the end. Now, at this point, I can figure out something very, very important. At this point, I know that because I have a bigger number of oxygen moles than I do nitrogen, I know that whatever subscript goes with the oxygen has to be bigger than the one that goes with the nitrogen, because I have more moles of oxygen than I do of nitrogen. So I know when I get done, the subscript on my oxygen has to be bigger than the subscript on my nitrogen, because I have more moles of that. Now, here's the problem. I could put 4.63 to 1.85, but here's the problem. I can't have 1.85 nitrogen atoms and 4.63 oxygens. Has to be whole numbers. So at this point, what can I do to get rid of those annoying decimals? Yeah, I'm going to divide everything by the smallest number. So, and I was a particular jerk when I made this problem up, I'm just going to tell you right now. Because when you take that 4.63 moles of oxygen and divide that by the 1.85 moles of nitrogen, you get 2.5. Sketchy, okay? I can't have 2.5 oxygen atoms to 1 of nitrogen. Oh, so what can I do? Well, if I change that to 2.5, and then I change that to 5/2, oh, that's cool. Now, Peyton, it's cool. You laugh, but it's cool. So, again, at this point, you're such a nerd if you think that's cool. But here's what this says, is that I have 5 moles of nitrogen to 2 moles of oxygen. Oh, that's kind of cool. Now that I know, because I know what that ratio is, now I know my formula is into O5. Okay? Now, here's what you're going to do wrong if you screw this up. You'll put the 5 with the oxygen and the N with the 2 with the oxygen. What?
You did that.
Yeah, we taught it that way.
What were you taught?
Multiply by 2.
If it ends in 0.5, you
Yeah, we
multiply
did.
if it's
everything
0.33, you multiply by 3, and if it's 0.77, you multiply by
there were so many
You gotta memorize all
But
of
this
it.
is why.
Oh, yeah. I remember that. That was so
I know I
stupid.
got it wrong.
It was
You didn't have a talking
It was like
Wait, what did you do again? Just the 2 times?
She literally
We just changed 2.5 to 5.2.
No, this is why, because it's a ratio.
That doesn't make sense.
What doesn't make sense?
Like the whole, well, you put 5 moles. Yeah, but why did you put the N next to the 5?
That was your fourth block?
Huh?
Look, the 5 has the N.
I think you just
5 moles of nitrogen, 2 moles of oxygen.
But you put into O5 over there.
Huh?
Look, they're switched.
Yeah, wait, yeah.
Oh,
That was supposed to be on top.
that should be nitrogen and oxygen.
Wait, so do you just keep it like,
You always divide the large by the
But
small.
1.85 is nitrogen.
That is so
Yeah, that should be nitrogen. And that should be oxygen. So,
okay.
it should be oxygen over nitrogen. So that's why you multiply by 2.
Stay after school.
Is because it works out, because it's an improper fraction. And if it had been, let's say it had been 1.33, okay, that would be 4/3.
Yeah, she never taught us that. We like had 0.6 you multiply.
That's weird. Yeah.
But this makes more, does this make more sense?
Yes.
Okay. That's why it's like, why are you all flipping out?
Yeah, Ed never taught us that way. She just taught us the weird way.
Oh, I'm going to have words with that young lady.
Don't take it from me. Don't take it from me. Tell her I said it. Tell her I said it. Yeah, tell her
Okay, I'll roll you under the bus. Okay. All right. Now, so when you get to that next part on the molecular versus the empirical, So basically, through another technique, typically you do this with oddly enough, with gas laws, okay? And you find the molecular formula. So what we're saying on that second part is that the molecular formula has a molar mass of 216 grams per mole. So if you find the molar mass of your empirical, if you find the N2O5, you take 2 times your 14, 5 plus your oxygen, the molar mass of this is 108. So 108 times something is going to equal 216. So if you figure, then if you get x by itself, you divide by 108, so x equals 2.
Oh, I know that.
So what do you do with the 2? Yeah. So then it becomes N4O10. Now, how can you check that that's right? Yeah, find the molar mass of N4O10. See if it's 216. If it is, odds are you did it right. If the molar mass of that is not 216, then it's wrong.
You're dissolving something with OH. How are you getting an acid?
I love
Okay.
potatoes.
All right. On number 11 with the redox, I want to make sure everybody's cool with the terminology. So, Leo says GER, right? You lose electrons, that's oxidation. Gain electrons, that's reduction. Now, where you typically run into trouble is the reducing agent and the oxidizing agent. So listen to me. Your reducing agent contains the element that is oxidized. Your oxidizing agent contains the element that is reduced, okay? So on your oxidizing agent, so let's start with this. What do you have for the element that is reduced? Hydrogen. What do you have for the element that's oxidized? Zinc. So the reducing agent contains what is oxidized. So what's your reducing agent? Zinc. Your oxidizing agent contains what is reduced. So what's your oxidizing agent?
Hydrochloric.
It isn't just hydrogen.
Hydrochloric.
It's hydrochloric acid. Your oxidizing agent is going to be that entire thing that contains what is reduced. So your oxidizing agent is hydrochloric acid. It is just not hydrogen, because the hydrochloric acid contains what is being reduced. Okay, anything else on that packet? Go on, let's go twice over. Get those handed in. Yes, hurry, run. Okay, so here's what we have next. And this is just going to kind of build on this whole thing of like acid-base equilibrium. So there's 3 different types of definitions of acids and bases. The first one is your classic, what I call the Chem 1 definition of acids and bases, called the Arrhenius definition. So on Arrhenius definition of acids and bases, this is the simplest one. Your acids start with hydrogen, like hydrochloric acid, nitric acid, sulfuric acid, acetic acid, okay? So you recognize acids as starting with an H, okay? Bases contain hydroxides, okay? Lithium hydroxide, strontium hydroxide, potassium hydroxide, okay? So that's the simplest definition. It works as what I call the Chem 1 definition of acid and bases, okay? Now, the more advanced one is what's called the Bronsted-Lowry. Now, here's the significance of the timing when the Bronsted-Lowry definition came into place. This came into being in 1923, 100 years ago, okay? 100 years ago from now is when this came into being. Now, here's the reason why that was significant. Because the Bronsted-Lowry definition of an acid is that it's a proton donor. Bases are proton acceptors. The reason that couldn't have come into being before that is because we didn't know that protons and electrons existed. Okay? So you couldn't have the Bronsted-Lowry definitions of acids and bases in the 1800s, when there no protons and electrons existed. Okay, so that's the significance of the timing of the Bronsted-Lowry. They had to have figured out the protons, which is, by the way, even though we teach this in chemistry class, everybody that figured out the structure of the atom were all physicists, because they were basically out of a job because they had figured out gravity, and they said, okay, let's find the structure of the universe. And so that's the way they took that on. Now, so here's the deal. So this still works. So let's say, for example, you put hydrochloric acid in water, okay? This is where you get into conjugate acids and conjugate bases as well. So if you take hydrochloric acid and you put that in water, what you get is the hydronium ion and the chloride ion. Strong acid, it ionizes completely, it ends up over here. So remember how this is existing is that you have this chloride anion, which has an extra electron, so it has this 17 protons surrounded by 18 electrons. It has this huge dome of negativity surrounded by the electrons. And out here is an H+. H+ is just nothing more than a proton. So basically, struck out there in the nether regions is this single proton going doo-doo-doo-doo-doo-doo. Because his electron is left, it's hanging out with chlorine. Okay? So the proton is just hanging out there going, doo-doo-doo-doo-doo-doo. What do I do? What do I do? So along comes the water molecule. Okay? Water molecule comes along and says, hey, I got a negative end. That proton out there says, hey, screw you. You don't like me. I'm going to go hang out with the water. Chlorine says, is all put off, and it says, okay, fine, I'm just going to hang out here by myself because I'm more stable that way anyway. So you show up to prom, you ionize completely. So this also fits the definition. So this is an Arrhenius definition of an acid because you have hydrochloric acid. But it also fits the Bronsted-Lowry definition because this is a proton donor. So in this situation, water acts as a base. And you're sitting there going, whoa, 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 whoa. Bases should have like hydroxide. They should be lithium hydroxide, sodium hydroxide, something like that. But this is a broader definition of it. So the water here acts as the base because it's going to take in that proton. So water in this situation acts as a base. Oh, that's kind of weird, right? It doesn't contain hydroxide. But by this definition, it is. It's a base. So this over here, you always create what's known as a conjugate acid. So this is the conjugate acid, and this is the conjugate base. So if you're trying to figure out which is the conjugate acid and which is the conjugate base, figure out which one gives up a proton to go back to its original form. So the conjugate acid is going to be H3O+, because if it acts as an acid and goes back in time and you reverse the reaction, this would give up a proton to go back to water. This would act as a base and accept a proton, go back to being HCl. So whenever you have a Bronsted-Lowry acid base, you also, by logic, you also form a conjugate acid and a conjugate base. Okay? So, boom, here you go. Now, the cool thing about this is, let's say you have ammonia, NH3, and you put that in water, you get NH4 and hydroxides. We'll spend a lot of time talking about this one. So in this situation, here's the cool thing about water. In this situation, water is actually acting as the acid. Because in this situation, the ammonia comes along, and that's a nitrogen surrounded by 3 hydrogen atoms. And we'll spend a lot of time talking about this structure. So the ammonia comes along to the water and says, yo, sup, I want one of your protons. The water says, whatever, go ahead. So the water gives up a proton, and you form NH4, but then what's left over are hydroxide ions. So here's the difference. If you put hydrochloric acid in water, you generate hydronium ions, and the pH goes down. because you're creating more and more and more hydronium ions. You're taking the negative log of a bigger and bigger number. If you put ammonia in water, your pH goes up because you're generating hydroxide ions, okay? So this is why water is said to be amphoteric. Depending upon the situation, water could act as an acid or water can act as a base. So in this situation, ammonium would be my conjugate acid because it would give up that proton to end up back at NH3. Hydroxide is my conjugate base because it would take in a proton and end up back at water. So when you're writing conjugate acids and conjugate bases, you have to pay attention to the charges on those ions, okay? You have to pay attention to that. Okay, so on your assignment. The first half of this is basically a summary of everything that we've just gone through. So don't flip out over that part of it. And yes, you're going to have some of this is going to come out of the textbook as well.
I'm getting AP physics class back, so.
I don't think she wanted that.
Okay, so for those of you that are new to me, and for some of you that have been a while before you've been in my class, here's the story. Here's your sheet of paper. Draw a line down here, maybe like an inch over. What I want is I want the answers here, and I want the work that generates them over here. Okay? So when you get to, like for example, a lot of these are ones that you're just going to write out. So like number 1, 2, 3, okay? Those are just answers that you're going to write out. So you can just write across like this. Leave spaces in between. So like when you get to number 6, solution has a pH of 3.45. Determine the following: the hydronium, hydroxide ion concentration to POH, and determine if it is acidic or basic. So like on number 6, here's what I would want. Hydronium ion concentration equals blank. Hydroxide ion concentration equals blank. Okay? Put the answers to the left in the work that generates that over there. My eyes are getting older. Okay? They've seen a lot in 56 years. Do not view your work through your eyes. View them through the eyes of a 56-year-old man who's trying to keep his blood pressure low. When in doubt, if you don't know how to do this and space it out, look at Gracie's paper. Okay? Because she does a beautiful job of keeping things spaced out. Okay? Literally. If you want to see how I want a paper done, look at Gracie's. Now, when you get to this backside and you have some questions out of your book, I tell you, and these are all about rice charts, when you get to question number 62, this is the one time you've got to work this thing as a quadratic. Because when you set up that rice chart at number 62, this will make sense when you get to it. And you set up that rice chart. When you subtract x, that x is so big that it actually alters the concentration. So only on 62 do you have to solve it as an actual quadratic. I gave you some hints along the way. Okay, I'm done.